All right, so let's continue then. So we started to talk about binary block codes, which is takes a number of input bits and produces a number of output bits. We talked about linear block codes, and linear block codes are such that if we take two code words and add them together, modulo 2, you get another code word. And this is true for any pair of code words. And we talked about systematic block codes, and systematic block codes is when the first bits in the code word is equal to the input to the encoder. So these are the information bits in the beginning. The last two bits in this case, or the bits that follows the information bits, are called parity bits or check bits. Okay. Now, we will send these, we will use these block codes for doing error detection, and errors occurs on the physical layer. So we talked about the physical layer a little bit, and a model of this is that we have some data, and then it's encoded into a code word. Okay, so we have some data and it's encoded into a code word, and these code words needs to be transmitted over the channel. So then we send these into a modulator, and then there is a channel with some noise, and then we have a demodulator. That we assume outputs some bits, and let's call them these bits y for the time being. Okay. Ideally, y should be equal to c. Now, due to the noise, we will make errors every now and then, according to the probability that we calculated earlier today, for instance. Okay. So every now and then, there will be a mismatch between these bit patterns. And one way to simply model this is to take the input bits, C, and then add modulo 2 a pattern, a bit pattern, which an error pattern that tells us which bits have been in error. Okay, so y. So y, the output, is equal to c modulo 2 addition with e. And e then is a binary pattern, and wherever there is ones in the e vector, the corresponding bits in c are flipped. Since modulo 2 addition with 1 flips the bit. Right? So suppose E is equal to, and let's take an example, say 0, 1, 0, 0, like this. Then this tells us that the second bit in C is flipped. i.e. is in error. And we see this that, for instance, if now C happens to be 0, 1, 1, 0, and then we modulo 2 addition to with we take E, which is then 0, 1, 0, 0, and we modulo 2 add these, we get y equals 0 plus 0, that's 0, 1 plus 1, that's 0, 1 plus 0, that's 1, 0 plus 0, that's 0. So we see that the second bit here is in error. Okay. So the number of ones in E tells us how many errors have occurred. Their position tells us where the errors have occurred. Okay. So was this reasonably clear? Okay. So then we will model the physical layer with this error pattern and see what we can do with this. Okay. And what we want to do is error detection. Okay, and what is the idea with error detection? The error detection is the following, that looking at y, can I detect if errors have occurred or not? That's my task. Okay, so can you tell me how to do this? So, for instance, if I'm the error detector and I get y, I know I get y, I get the bits. How can I tell if an error has occurred or not? Yes?
If you know all the possible values that y could be.
Exactly.
It's not one of those, then it's wrong.
Okay, very good. So the idea is that we look at y here, and we know that what was transmitted was a code word. And if y is not a code word, then we know something has happened, right? And if we look at the code word here for this rate 1/2 code, we have 4 bits here, but we don't have all 4-bit patterns. We only have 4 of these. Okay, and there are 16 4-bit patterns, right? So as long as y is not one of these code words, then we know for sure that an error have occurred. Right? So I'll say that again, but because it's super important, right? We know that we transmit one of these code words. The receiver does not know which, okay? But it knows it's one of these 4. If y turns out to be not one of these 4s, we know that an error has occurred. Okay, and then we flip the argument and say, okay, now suppose y is a code word, then we will accept that and say no error has occurred. Okay, so to summarize, if y is a code word, so if y is in this curly C, if y is not in curly C, then declare error. Okay, then we say y is in error. There are some bits in y which are in error. We don't know which, but for sure it's not what was sent. We know this. Then, if y is a code word, then we say declare no error. Okay, so as an error detecting circuit, we have 2 choices. Either to accept the bits or reject them. So we reject or accept. Here we are quite certain that an error has occurred. But let me ask you this. Are we sure here that no errors have occurred?
No.
No, exactly. What could have happened? Well, it could be that we have transmitted a code word, that is one of these rows, and E is such that it moves from one code word, a transmitted code word, to another code word, right? And that error will not be caught by this logic. Okay. So there is a possibility of failure in the error detection circuit, and that turns out to be a really bad thing for various reasons. So we would try our best to avoid this case, but inevitably things go bad, right? So sometimes we will accept bits even though errors have occurred. And later on we will talk about what the consequences this might have. But essentially what it means is that we need to somehow be able, when we write applications that run over networks, that every now and then we get faulty data, and we can never trust really 100% the data we get. Okay, we just have to deal with it. Okay, so this undetected errors is serious, and let's see. Okay, and let's return to that a little bit and make an example on how to do this error detection in an efficient way. Because for real codes, it's not practical to have a table of this because it scales very badly with k. So k here could be, for instance, it could be 8,000 bits or something like that. And then 2 to the power of 8,000 is a humongous number, right? So we can never construct that table. So we need a more efficient way of checking whether this received 12,000 bits or 8,000 bits, whatever, is it a code word or not? And we'll talk about a few things on how to do that. So if we have these systematic block encoders, there is an easy way to check whether a pattern is a code word or not. And it's basically to re-encode the data bits at the receiver and check whether this corresponds to what we have received. Okay, so the idea is the following. We have some data bits, and when we do encoding, we put the data bits in the beginning of the code word. And then we have a circuit which calculates the parity bits, and these we put in the end. Then it goes over the channel, and then we get the received bits y here. And y, the first k bits should correspond to the data bits, and the last n minus k bits should correspond to the parity bits. Both of these might be in error, we don't know. So that's our objective now. Can we check y to see whether this is a valid code word or not? And the principle is the following, is that we take y and we split it up into two parts. The n bits, okay, so these are k bits and these are n minus k bits. So we take, in y, we take the first k bits and we put them up here, and we calculate the check bits corresponding to this input bit pattern, and then we get some parity bits. Let's call it p prime. Okay. If there are no errors in the data bits, p prime would be equal to p. You see this? Data coming in here, and that produces p. Data coming in here producing p prime. If there is no error here, then the input to this check bit calculator here is exactly the same as the input at the transmitter side. And therefore p would be equal to p prime. So sorry, p prime would be equal to p. Okay with this? All right. So basically what we need to do then is to check whether p prime is equal to what we have received. And if there's no error in the parity bits, then p prime would be equal to p, and everything is okay. Then we know that what we received is actually a code word. So, since we have a systematic code, we know that the first k bits defines what the last n k bits are. So we basically check that this relationship holds. If that relationship holds, it's a code word. If it doesn't hold, it's not a code word, and then we reject it. So if we continue with our favorite code here that we have just drawn up here. Now suppose, we don't know this, but suppose the data was 0, 1. That means that the transmitted code word is what? Okay, I go in 0, 1, it should be 0, 1, 1, 0. Okay, so the code word is 0, 1, 1, 0. Now suppose E is equal to 0, 0, 0, 1. Then Y, the received bits, would be the same as we transmitted, except that the fourth bit will be flipped. Okay, this I can deduce from the error pattern here. So it would be 0, 1, 1, 1. Okay. Now, my job as an error detection circuit here is to look at these 4 bits and decide whether this is a code word or not. Okay. We already know it's not a code word, but just to illustrate how this works, we isolate the first 2 bits here and go into our table here and compute the parity bits. So I have a circuit that can do this calculation, that can go from information bits to parity bits. Okay, and what information bits did we have? We had 0, 1. So I go in here, 0, 1, calculate the parity bits, it's 1, 0. Okay. Okay. So the information bits, or the first 2 bits here, allows me to calculate the parity bits. And then I check these parity bits and see, do they correspond to what I have received here? And they don't, right? And therefore I say, error, like this. Okay. So again, just to repeat, I receive these 4 bits. My job is then to check whether this is a code word or not. If I have access to the circuit that can calculate parity bits, I simply input the 2 bits, the first 2 bits here, which hopefully is data bits, and then produce the parity bits that corresponds to this, and check whether these parity bits is what we have received. And in this case, no. Now, here the error occurred among the parity bits, but we see that even if the errors occur in the data bits, we will not be able to compute, the thing works still. I hope you see this. So it doesn't matter where the error occurs in this case. Okay? Okay. Now, suppose we have another error here, which is 0, 1, 1, 0. What does that let us, what is y in this case? Well, we transmitted, we transmitted this, and the error pattern is such that we should flip the second and the third bit. So what we get here is 0, 0, 0, 0. You see this, I hope? So 0 works, flip the second bit, flip the third bit, and then keep the fourth bit. So 0, 0, 0. Repeat this, take out the first 2 bits, go into the circuit and input the 0, 0 here, and out comes the parity bits, which happens to be 0, 0 in this case also. So P prime here is 0, 0. Okay. So what do I do in this case? Do I declare an error, or do I declare no error? No error, exactly. Because these 2 bits, the parity bits I just calculated locally at the receiver, corresponds to what I received. So I think everything is okay. So, no error. Okay. Even though there was an error. Okay. So this error pattern is such that it's not detectable. It's an undetectable error pattern. And these are These are bad, right? They cause many difficult problems. Okay. So can we say something about what are those? Can we say something about if we have linear block codes? Can we say something about what patterns, exactly what patterns are undetectable error patterns? As a matter of fact, we can, right? And let me show this for you. Remember that when we had a linear block code, we can go from code word to code word by adding another code word. Okay. So, for instance, suppose we transmitted this. Okay. Then there are a few things that could happen. I can get an error can occur, and I can get a pattern which is not a code word. Right? This will be detected. It could be so that I get no bit errors whatsoever, and then what I receive is what I transmitted. Okay? Then the bad events can occur. And the bad events is that I go from this code word to another code word. For instance, here, here, or here. These are the three undetectable error patterns when we transmit C1. Okay, because I go from one code word to another code word. And what are the problematic undetectable error pattern when I go from here to here? Well, it's C3. Going from here to here, well, it's C4. Going from here to here, well, it's C2. It's the other code words that are undetectable. Okay, is this true in general? Well, let's see. Suppose we transmit C2. If there is no error, that's okay. We go back here, and we declare no error, and no error has occurred, no problem. We can go out here somewhere in space. This error will be caught, but the problematic things are when we go from C2 to C4, to C3, or to C1. I.e., when the error pattern is C2, C4, or C3. And we can repeat this for everything. Okay? So for the linear block codes, the undetectable error patterns are the non-zero code words. Zero code word is no problem. It's not an error, right? It's all zeros, no errors. So the all zero code word, you just loop back to where you started. Okay. So was this clear? This is actually a pretty important point. That we will have undetectable errors, and the undetectable errors we have are the non-zero code words. Okay. So, can we say more about these code words and how we should choose them and so forth? Yes, we can. And let me introduce a little bit of a notation here. There's something called the Hamming weight. Have you heard of this before, Hamming weight? I mean, it's basically like this. If you have a vector of elements, the Hamming weight is the number of non-zero elements in that vector. So the Hamming weight is the number of ones in a binary vector. So W here for weight, H for Hamming, U for the input vector, and then it's number of ones in U. Okay, very simple. The Hamming distance between two binary vectors is the number of positions in which they differ. Okay. So the Hamming distance between u and v is the number of different bit positions in u and v, which is the Hamming weight of u plus v. So if u, for instance, is equal to 1, 1, 0, 1, like this, the Hamming weight of u is equal to what? Three. Very good. If v is equal to 1, 0, 1, 0, like this, what's the Hamming weight of v? 2. What is the Hamming distance between u and v? 3, right? Because why? Because they have the same first position, but they differ in the second, third, and fourth position. So they differ in 4 positions, which is 3. But if we take u plus v, what do we get? Well, we get 1 plus 1, that is equal to 0, and then 1, 1, 1. So we get 1s in the positions where u and v are different, and 0s when they have the same bit. Okay, so the Hamming weight of u plus v is equal to 3, which is then the Hamming distance between u and v, like this. Okay? All right. So Hamming distance is, it's like Euclidean distance when we have vectors, real dimensional vectors in the 3-dimensional space or 4-dimensional space or whatnot. But the Hamming distance is tailored then to binary vectors. So it's a distance metric. Okay, so the minimum distance of a code is an important parameter. And let me try to explain why this is the case. So the minimum distance of a code is that we take 2 codes, 2 code words, and we compute the distance between them. And then we search among all pairs, and we take the smallest distance between two distinct vectors, and that's our minimum distance. So we search over all pairs ck and cl in the code, k not equal to l, and then find the minimum distance, which is also then the minimum distance of the Hamming weight between ck plus cl. That's only by definition from the Hamming distance. Okay. Then we know that for a linear block code, ck plus cl is another code word, right? So this is, for instance, equal to cj. So for linear codes, we can find the minimum distance by finding the code word with the minimum weight. Okay, minimum number of bits, 1 bit. Okay, so a little bit like visually, if we have these code vectors that are placed out here in space somehow, then we calculate the distances between these two, and we see that C3 and C2 are the closest one. So the Hamming distance between these two is the minimum distance. Now, if we transmit C2 and we have a certain error, then our received vector y will be at the tip of this, will be at the tip here, right? So this is y. Will that be detected as an error or not? Given y, would the error detection say this is an error or this is fine? Well, in this case, it will say, yeah, there is an error, right? Because y for sure is not a code word. Okay, so y, no, this looks bad. Something bad has happened. I know I sent C1, C2, C3, or C4. I get something which is neither. An error must have occurred. And we see then that, okay, E here is detectable if Y, which is C plus E, is not a code word. So this is what we said already, right? As long as the error is such that when it takes a code word, it doesn't reach another code word, then it's detectable. So if we put the same error on all of these code words that we have, we never get another code word. So y in all these 4 instances is not a code word. Okay. And if we put circles around all these code words at the minimum distance, we see that if the Hamming weight of the error is less than the minimum distance, then E is detectable. Okay. So this is a quite important conclusion here. All right? Because whenever I start, I can only move so far away from this code word. And as long as I move less than the minimum distance, I can never reach another code word. And therefore, all of those error patterns are detectable. Okay. If the Hamming weight is greater than d min, we might have an undetectable error. Right? So, for instance, this is an undetectable error going from C3 to C2, but we could definitely have another error like this, which is quite much larger than the minimum distance, but it just ends up in the wrong place. Okay. So we need to be quite unlucky if we get one of these, or we hope that this will not happen very often. Okay, any questions on this? So then, if we then continue here with our example code, what can we say about what is the minimum distance here? Well, I mean, we can start to compute distances between all these code words and try to find them, but since we know that we have a linear block code, we only need to look at the Hamming weight of each of the code words here. Okay, so the Hamming weight of the code words. So what is the Hamming weight of this code word? 0. And this 2. This 2. This 4. So what is the minimum distance for this code? Any takings on this? 2? Yeah. So, I mean, the 0 code word will always have 0 weight, right? So that doesn't tell us what the distance is. So if you look here, we search among all code words and compute the Hamming distance of that, and we exclude the 0 code word, and that will be the minimum distance. So the minimum distance here is equal to 2. Okay, so what can we say about detectable error patterns here? Well, we can say that all 1-bit patterns are detectable. Right? Right? Because there cannot be the minimum distance, as long as we're less than the minimum distance, we will be fine. As a matter of fact, we can say way much more here. We can say that since no code word has weight 3, all 3-bit error patterns are detectable also. The 4-bit errors is not detectable. We see that we can be unlucky if we have a 2-bit patterns. These 2-bit patterns are not detectable, but there is a bunch of other. I think there are 6 other 2-bit patterns which are detectable. Right? So these are the undetectable errors, and everything else is detectable. Right? The code words are the undetectable error patterns. These are the undetectable error patterns. Okay, so that is about the theory of block codes. Let's try a few examples and see how they play around. So these are examples of codes which are used in practice, and as usual, they're have different complexities and different performance. So the simplest error check code we can think of is the singularity parity check code. And singularity parity check code has a single parity code, okay, so which means that n minus k is equal to 1. Okay, and it works like this. If we have k input bits, we just add them together, modulo 2, and that is our parity bit. Okay, and this means that the parity will be 1 if the number of ones in D is odd, and 0 if the number of ones in D is even. And that means that the code words, which consist of all these bits and the parity bit, will always have even weight. So if we add all the bits together in the code word, we get P0 plus P0, and that's 0. So even number of ones in a code word. So to check whether a bit pattern is a code word, we just count the number of ones in it. If it's even, then we say it's okay. If it's odd, we say it's an error. Okay, because we know that there are no code words which has an even odd number of ones. Code rate is quite high. It's 1 minus 1 over k. Minimum distance is 2. So it can fix all one single bit errors. Okay, because if you have a single bit error, you go from an even number of ones to an odd number of ones. Okay, which is not a code word, so we can fix that. As a matter of fact, we can detect every bit pattern which has an odd number of ones in it. 1, 3, 5, 7, etc. But all even, we're screwed. So 2, 4, 6, 8. Then we have undetectable error patterns. So simplest code imaginable, but also not super good. This works very well if we don't have a lot of errors in a code word, where errors are very, very rare. There is something called the internet checksum, which is an extension of this idea, and it catches more errors. It's also something which was used in the early days of the, it's still in use, but it was put into use in the early days of the internet, I mean in the 60s and 70s. Okay, so it's used now still for error detection in TCP, UDP, and IPv4 headers. Okay, so it's still in use. And the reason why it's still in use is mainly from historical reasons. Nowadays, it would probably not have been put into place. The idea was that this was a code where we could do encoding and decoding very efficiently with the type of hardware that was available at that time. So it works like this. We have data, and we split that into 16-bit blocks, or 2-byte blocks is the same. And then we pad with 0 bytes if needed, or bits also, I guess. So then we have D, and we divide it into 2-byte blocks. Then we add these blocks as 16-bit integers using ones complements addition. Okay, I will explain what that means later. We denote that with 1 plus an apostrophe here, so 1 tick, plus tick, I mean. Okay, and the 16 parity bits is found by adding all these 16-bit blocks from the data using one complement, and then we modulo 2 add FFF to this, which is basically flipping all the bits in the sum. Okay, and that's our parity bit. Okay, so this is just a method which is used. Block the input bits, add them with one's complement, flip the bits, and then we had the parity bits. It turns out then that if we take the code word and would like to compute the parity bits using all of this as data, it will have an internet checksum of 0. So that's one way of checking this also. That we get a bunch of bits here, and we treat all of that as data, and we go through this, and then we would get 0 as an internet checksum, and then we know that we have a code word. Okay. Alternatively, we can compute P from D and then check whether these are the same, as we did earlier. This one complements addition. It is what it is, so to say. And the thing is that when we add bits together, if we add two 16 bits with normal addition, we can sometimes get a carry. So we get a result which is 17 bits. That's not so nice. We would like the number of parity bits to be 16, not 17. So what we do then is that we correct for this. So if I have n-bit integers, a and b, and I add them, if a and b is less than 2 to the power of n, then they fit in a 16-bit word, and I leave them alone. So then the result is a plus b. If a plus b happens to be greater than 2 to the power n, meaning that they need 17 bits in order to be represented, I take a plus b and then subtract off something that makes it fit into 16 bits. And it turns out that 2 to the power n minus 1 would do nicely in this case. So if we want to make an example of this, so if we have 8-bit integers, 255 in base 10, or E1 in base 16, or this bit pattern, so this is in base 2, and this 155 in 10, base 10, 9b in hex, and this bit pattern in 2. If we just use regular, as you, in your calculator, 225 plus 155, you get 380. And 380 is greater than 2 to the power of n. So what is 2 to the power of n? Well, it's 256, right? So 380 is more than 256, and therefore I subtract off 255. 2n minus 1 is 255. So subtract off 255, I get 125. This will fit into 8 bits. Okay, I could have done this 16 bits, but there's too many, too long numbers. If we do this in binary, we can do the same thing. If we get a carry, we actually put it down here and we add it like this. So if you want to do your addition in binary, you do this. Or if you do it in hex, it's the same idea. You add these hex numbers, you get a carry of 1, you put it there, you add it together, you get 70. And 125 has this representation in binary, base 2, and this in hex. So, I mean, it depends on what you used. Okay. So that about internet checksum. And here's an example on how to do that. Okay, let's do it. Okay, so here is the data. We split it into groups of 16 bits. So we have the red bits, the blue bits, and the green bits. We group them into 16-bit integers, and then instead of writing a lot of ones and zeros, let's put them just in hexadecimal like this. So 46AA are these bits, and then so forth. Then we add the digits as normal integers. So then, and we get 1 9CF4, 9C54, 9C5F, okay? And in decimal it's like this. And here we have a carry, okay? So this we need to take care of. And we just wrap this around, so we take 001 plus the result, and then we get a new number, and this would fit into 16 bits. If we want to do that in decimal, it's going to be like this. And then we negate, that is to flip the bits to find P. So P is FFF, modulo 2 addition to 9C60, and then we get 639F. Okay, so you can do this at home if you're bored. So here we have our parity bits. So we add that at the end to the code word. Okay, so this is a systematic code where we calculated the parity bits and we put that in there. And then to check whether this is a valid code word or not, one way to do that is to go through the same motions as we did before, treating the parity bits as data bits, and then the result of the parity calculation should be all zeros. So if one add everything together, we get this. We do a wraparound carry, we get FFF, and we take FFF and we negate that with FFFF, and we get 0. And then we know this is a code word. Okay, so at the these calculations here is done by the receiver to check whether whatever bits we got is a valid code word or not. But I think that's it for today. Lagging a little bit because the next time we will talk about the best, not the best, but the error detection code which is heavily used in practice if we're interested in high performance. And these are known as cyclically redundancy check codes, or CRCs. Maybe you've seen them before in other contexts, but we'll talk a little bit on how they work and how they're constructed, and how we can check for how we can do error detection using these. But let's do that on Monday. So have a nice weekend.